In this video, we're going to do a basic overview of the concepts of power functions and polynomial functions. A power function is a function that can be written as f of x is equal to k times x to the power p, where k and p are any real number. Notice that there's only one term here for this to be a power function. P can be any power that we want. So P can be any real number. The other type of function we're going to look at in this section is a polynomial function. It's a function that can be written like f of x is equal to an x to the nth power plus an minus 1 x to the n minus 1 power plus so on and so forth, a1 x to the first, a sub 0. The coefficients a sub n minus 1, a sub 1, a sub 0, and so forth, they are all real numbers. And we make sure that our coefficient a sub n is not equal to 0. Because if it was equal to 0, then I could have made this polynomial function smaller with less terms. The other thing about polynomial function is that the power of n has to be a whole number. So it has to be a positive integer, or a non-negative integer, I should say. And then n minus 1 is also a whole number. This is x to the first, that's also a whole number exponent. When I don't see any x, that's like an x to the 0, and 0 is a whole number. Let's look at a few examples and determine if these are polynomial functions or not, and also determine whether these are power functions or not. Let's start with this 6x squared. Well, we have x being raised to a power and a coefficient out front. So it is a power function. Also, because we have x to a whole number power, it's also a polynomial function. So this first f of x is both a power function and also a polynomial function. This second f of x, which is 4x to the square root, 4 times the square root of x, that actually can be rewritten as 4 times x to the half power, or 4 times x to the power of 0.5. Therefore, it has the basic function, or the basic form of a power function, constant times x to a power. So this is a power function. But it is not a polynomial function. Because x is raised to a power which is not a whole number. That 0.5 is obviously not a whole number. So it's a power function, but not a polynomial function. And this third function works the exact same way. We have constant times x to the 1.5 power. So that fits the power function, but it is not a polynomial function because our exponent is a 1.5, and 1.5 is not a whole number. For this last function, the x variable is in the exponent, and that is not a power function. So it's not a power function, and also it's not a polynomial. Again, for it to be a power function or a polynomial function, our x has to be, cannot be in the exponent. And so since the x is in the exponent here, it's not a power function and not a polynomial function. So a power function has to be a single term where we have real number times x to any power that we want. Polynomial, we have to have whole number terms, whole number powers on the x. Notice we can have multiple terms in the polynomial function. Let's do another example. Here we have f of x is equal to 3x to the fourth plus 5x to the third minus 6x squared plus 8. And then a function whose output is 12x to the fourth plus 3 times x to the 8.2. And then a function whose output is 9x to the negative 3 power. Go ahead and push pause on the video and determine whether each of these is a polynomial function, and then whether each of these is a power function. I'll show you how that's done right now. So we have 3x to the fourth plus 5x to the third minus 6x squared plus 8. Notice that with every power on our x, it is a whole number. We have 4 different terms here. So this is a polynomial function. So it is a polynomial function. However, it is not a power function. Because a power function only can have one term. If this function only had that first term, then it would have been a power function. But since it has these other 3 terms, it cannot be a power function. So power functions have to have single terms. Once we've seen that, it's pretty obvious that this second function is not a power function either. And it's also not a polynomial. That is not a polynomial function. Not a polynomial function because x on the second term is being raised to the 8.2 power, and we need whole number exponents for it to be a polynomial function. It's not a power function because it has multiple terms. So this one is not a polynomial function and also not a power function. This last function is not a polynomial function because the exponent is a -3. We need whole number exponents. -3 is not a whole number. It's an integer, but it's not a whole number. A whole number has to be non-negative integers. So 0, 1, 2, 3, 4, but all 0 and positive integers. So it's not a polynomial function because of the negative exponent. It is a power function. Having a negative exponent is perfectly fine with a power function. So we see that there are some functions which are polynomials but not polynomial functions but not power functions. There are functions which are neither power functions nor polynomials. There are functions which are not polynomials but which are power functions. And earlier we saw a function which was both a power function and also a polynomial function. So we can have functions of any type. They could be polynomial functions or power functions, or neither or both. The reason why we're focusing on these polynomial functions and power functions is because they are nice types of functions that we're going to use in this section of the material, especially polynomial functions. Now, let's say we have this general polynomial function. F of x is equal to a n x to the n, and so on and so forth, such that a sub n is not equal to 0. So the lead coefficient is not 0. Well, if this coefficient is non-zero, we call that the leading coefficient. That is the coefficient on the term where we have x to the highest power. That's our lead coefficient. And that highest power is called the degree of the polynomial. So a sub n x to the n gives us the degree of the polynomial and also the leading coefficient. And this is important for investigating how polynomial functions work. Knowing the lead coefficient and the degree actually tells me the shape of the polynomial function, or at least part of the shape of a polynomial function. So let's take each polynomial and determine the degree and leading coefficient of that polynomial. By the way, hopefully we know that a polynomial function is a function whose output is a polynomial. This expression is a polynomial expression just called a polynomial. So a polynomial function has an output which is a polynomial. And in this example, we're just saying if the output is this, what's the leading coefficient and the degree of the polynomial? Again, we could have said what's the leading coefficient and degree of a polynomial function if this were the output of a function. It goes pretty fast in each of these cases because in each of these cases, the terms are in descending order, meaning the degree of the first term is higher than the degree of the second term, is higher than the degree of the third term, and so on and so forth. So the lead coefficient is pretty obvious to pick out. It's the 3, and the degree is the 4. So degree is 4. The lead coefficient is 3. By the way, most polynomials are written in this descending order. If your polynomial was not written in descending order, let's say we write the 3x to the 4th term as the 3rd term of the polynomial. That doesn't change anything on the degree and the lead coefficient. The lead coefficient is still 3 because that's the coefficient of the term of highest degree, or with the highest x power. Highest power on x, excuse me. And that highest power on x is the degree. So regardless of the order of the terms, the lead coefficient is still 3 in this first problem, and the degree is still 4 in this first problem. In the second problem, the degree is 5. Clearly, we have an x to the 5th term, and the lead coefficient, that's the coefficient on x to the 5th, which is an implied 1. Lastly, we have 9x to the 6th, so the degree of that polynomial is 6. The lead coefficient of that polynomial is 9. So there we go. Now we can easily identify the degree and the lead coefficient of polynomials. The reason we're identifying the lead term and the lead coefficient and the degree of polynomials is because we eventually want to take something from that polynomial and understand the graph of it. Now, before we get to polynomial functions and their graphs, let's talk briefly about the graph of a power function. Let's take a power function f of x is equal to x to the p power. Well, there's lots of different shapes of a function like that depending on the value of p. In fact, let's turn to Desmos and investigate some of those shapes. Notice, by the way, I left off the coefficient of k. I'll put that in just so you see what that does in a moment. But let's investigate these types of graphs. I'm going to manually type in the different powers. So right now I have f of x is equal to x to the 0th power. That's a constant. X to the 0th power is just 1. So that's like y equals 1. So we get a horizontal line in that case. If I put in x to the 1st power, then I get a line through the origin. If I go x squared, I get a parabola. X to the 3rd, well, that gives me the shape of my basic cubic function. My basic x to the 4th kind of looks like a parabola, but the way it differs from a parabola is down here, it's closer to the x-axis for a longer period of time. So if I graph two functions side by side, our x to the 4th and our x squared, you can see that the x to the 4th kind of stays closer to the x-axis and then it zooms up a lot quicker. So it increases a lot quicker. But same basic idea is that on one side it's going off to positive infinity, on the other side it's going off to positive infinity. What if we have an x to the 5th? Again, this kind of looks like an x to the third, but it's steeper than x to the third. X to the sixth, again, kind of looks not quite parabolic, but that general shape where both sides are going to positive infinity. X to the seventh, again, one side's going down to negative infinity, one side's going up to positive infinity. So when we have positive exponents, positive whole number exponents, it's pretty straightforward what that power function looks like. Now, if we have other exponents, something like x to the 1.5, then it's not so clear. We get this shape, which has a little bit of curve in it. If I go x to the 2.5 power, I have this shape. Notice that we can't plug in negatives because the 0.5 is basically a square root. But if you did something like x to the 2.4, well, that does have both sides. Notice that this is kind of parabolic shaped looking. And then you could also do exponents which are less than 1 but more than 0, something like 0.2. We get this shape, or 0.3, we get this shape, 0.5, we get that shape. That's our base square root function. We could also have negative exponents. Negative 1 looks like this. Negative 2 looks like this. Negative 3 looks like this, and so on and so forth. Negative 0.5 gives this graph. Negative 2.5 gives this graph. So we get lots and lots of different shapes with those different exponents. We are going to focus most on positive integer exponents for just a moment, because that's where, when I have positive integer exponents, that's where the polynomial functions and the power functions overlap with positive integer exponents. And I know I haven't done this before, but x squared, if I multiply that by any coefficient, let's say 4, all I do is vertically stretch my graph by a factor of 4, or in this case, I multiplied by 5, that would be a vertical stretch by a factor of 5. If I put a negative in front, then I just flip the entire graph upside down. That's the same thing if I have x to the third or x to the fifth as well. X to the fifth looks like this. If I put a negative in front, I just flip it upside down. So we see we get lots of shapes depending on powers of p, but there's just a couple of shapes when p is a positive integer. If p is a positive even integer, then we get the parabola looking shape where both sides, both the left and the right side, are pointing upwards. Again, that's with positive coefficient here of 1. If we put a negative in front, then we'd both be pointing downwards. And if p is a positive odd integer, then we come from a y value of negative infinity, go up through the origin, and then go out to a y value of positive infinity. This looks like it's probably either x to the third or x to the fifth. F of x equals x to the third or f of x equals x to the fifth. So when we have an even, positive even integer, we get this cup shape where both sides are going off to positive infinity. When we have a positive odd integer, we go from negative infinity up to positive infinity. And we saw what happened if we plug in a coefficient here in front of the x to the p power. So this is what we describe as the end behavior of a graph. In particular, we're going to look at the end behavior of power functions where p is a positive integer. By end behavior, we're saying what is the graph doing as x gets bigger? In other words, as x gets bigger and bigger and bigger, what is my y value going to? As x goes to positive infinity, what does my y value go to? And then we'll do the same thing as x goes to negative infinity. That's sort of end behavior on the left-hand side. As x gets further and further and further away from zero, what's my y value doing? What's my corresponding y value doing? And the notation that we use is this. As x, and then we put right arrow, infinity, what does f of x do? That's saying as x is getting bigger, moving to the right, so as we're moving to the right, what does my output value do? And then as we move further and further to the left, as x goes to negative infinity, what does my function do? That's what we call the end behavior notation. And what we just saw was that if p is a positive even integer and k is positive, then as x gets bigger and bigger and bigger, my y value goes off to infinity. And then as x gets bigger and bigger and bigger on the left-hand side, in other words, as x moves towards the left, my function goes out again to positive infinity. Now, on the other hand, if this k is negative, and we have x to the p where p is even, then as x gets bigger and bigger and bigger, my function value goes off to negative infinity. As we move towards the left on the graph, my function value goes to negative infinity. That's if k is negative. On the graph, we can see that all we're saying is as the x value moves to the right, what's the y value doing? The y value is moving up to positive infinity as the x value moves further and further to the right. As the x value moves to the left, further and further to the left, the corresponding y value is moving up towards positive infinity. That's with even power and coefficient being positive. If we have an even power with a coefficient being negative, then as x moves towards the left, we shoot down to negative infinity. As x moves towards the right, we shoot down to negative infinity. Now, on the other hand, we saw that if we have our function, which is x to an odd power, that is positive odd power, then as x moves towards the right, the y value is going to shoot up towards positive infinity. As x moves towards the left, the y value shoots down to negative infinity. And it does the reverse if we put a negative in front. So that's the end behavior of a power function whose exponent is a positive odd integer. If the exponent is a positive odd integer and the coefficient is positive, as x moves towards the right, the corresponding y values go off to infinity. As x moves towards the left, the corresponding y values go to negative infinity. And it does the exact reverse thing if that coefficient were to be a negative. If the coefficient were a negative, then as x moves towards the right, my function output value goes down to negative infinity. As the x moves towards the left, the function output goes up to positive infinity. So now we know the end behavior when we have a power function whose exponent, whose power, is a positive even number, and we know the end behavior of a power function whose exponent is a positive odd number, positive odd integer. Let's quickly look at these three power functions and determine the end behavior of each. And we'll use the notation we've developed in the previous couple of slides. If you want to try this on your own, go ahead and do that. In a couple of seconds, I will do it on the computer. Without having to graph these by hand or by technology, I can see that this f of x has an even power. So positive, even integer as the power. And my coefficient is positive. So in general, I know it's going to point up in both sides or on both sides. Therefore, if x goes to the right, then my function value is going to go up to positive infinity. And as x moves towards the left, I know my function value, again, is going to positive infinity. For g of x is equal to x to the fifth. That exponent is a positive odd integer. We have a coefficient of 1. And so in general, I know it's going to look, I didn't draw this very well, but it's going to look something like this. It's going to start lower left, climb, and then shoot off to upper right. So as x gets bigger, the function value is going to go off to infinity. As x moves towards the left, my function value goes to negative infinity. And that's what we get. Now, if we have our h of x is not going to do the same thing as this one. In fact, because h of x has a positive odd exponent or a positive odd power, but h of x has a negative coefficient, we know that it's going to have the opposite shape as g of x. So g of x did this, h of x is going to do this. It's going to start in the upper left and move towards the lower right, whereas my g of x started in the lower left and moved up and to the right. H of x is going to start upper left and move to the lower right. So as x gets really, really big, my function value is going off to negative infinity. And as x gets towards negative infinity, my function value is climbing and going to positive infinity. That's the idea of the end behavior of these graphs, of these power functions. Now you'll notice that each of these power functions is also a polynomial function with one term. So a natural extension is to ask what would happen to a polynomial function with multiple terms. And it turns out that the end behavior of a polynomial function is the same as the end behavior of the power function, which has a sub n x to the n as the only term. In other words, if we have a polynomial function, as x gets really, really big, this a sub n x to the n is going to grow a lot faster than these other terms. And it's going to dwarf those other terms in terms of how fast it's growing. Again, this is the standard polynomial function, so we're saying that a sub n is not equal to 0. Otherwise, we'd have to rewrite this. Now, it's not going to necessarily do the same thing in the middle as this other function, as this power function, but it will do the same things on the end because as x gets bigger and bigger and bigger, this term overtakes all of the others. And the same is true as x goes to negative infinity. As x gets closer and closer to negative infinity, so it's going towards the left, this term is going to overpower or dominate these other terms. So the end behavior of a polynomial function is the same as the end behavior of the polynomial function who has a single term of degree n whose lead coefficient is a sub n. Let's look at this behavior. Let's look at these two examples and determine the end behavior of these two polynomial functions. We have an f of x and a g of x. If you want to push pause on the video and do this on your own, go ahead and do that. In a couple of seconds, I'll show you how the problem is done on the computer. Let's do these two. So the degree of this polynomial function is a 4. The lead coefficient is a -1. So I basically say the end behavior is like an f of x equals -x to the 4th. Again, this one was nice because it had descending order. We started with the term of highest degree, and then we went down from there. So the end behavior is like f of x equals negative x to the fourth. And we know that that's going to have end behavior because it's an even power. Both sides are pointing in the same direction. Because it has a negative coefficient, both sides are pointing down. So as x moves towards positive infinity, my function is going down. So we'd say function is going towards negative infinity as x moves towards the right. My function also goes to negative infinity as my function moves towards the left. So we have f of x goes to positive infinity on the right, f of x going to negative infinity on the left. For this second function, the end behavior is like, well, it's going to be like a function g of x, which is equal to just the leading term there, which is 1/4 x to the fifth power. That's an positive odd exponent. The coefficient is also positive. So we know the general shape is going to start lower left and move towards the upper right. So as x goes to positive infinity, I know my function value is going to positive infinity. In other words, it's moving up. If my x goes to negative infinity, then my function is moving down. So that goes to negative infinity as well. So determining the end behavior of a polynomial function is determining the end behavior of a power function of the same degree, of the same lead coefficient. Now, I want to talk briefly and just say this is the end behavior. Weird things can happen in the middle. I might have a lot of, weird ups and downs, and it could do something like that in the middle. It could, this one down here, could do something like, a couple of different ups and downs in the middle, and then do that. But the end behavior is going to be the same. As you move far enough to the right, it's going to go off to infinity. If you move far enough to the left, it goes down to negative infinity. So we could have some ups and downs. It doesn't always have to be a smooth curve. We could have some stuff going on in the middle, but the end behavior goes and matches the same as the end behavior of the corresponding power function. And just so you see that that is true, in these cases, I have graphed both of these. The f of x, as you can see, if you move towards the right and towards the left, we're going to negative infinity, shooting down there. But in the middle, it does this weird thing where it has a little hump here, goes back down, goes up, another hump, and goes back down. So there's some weird things going on in the middle of that f of x that I just said the end behavior for. As you move towards the left, move towards the right, we go down to negative infinity on both sides. But the middle behavior does some weird things, does some weird jumps and has those types of features. The g of x that I just did, if I scroll out far enough, it's hard to see here, but you see the end behavior as you move down, excuse me, as you move towards the left, you move off to negative infinity. As you move towards the right, you move to positive infinity. But there's some really strange things going on in the middle. We have this thing where we go up, goes all the way up to, like 257 or something like that, and then comes back down and does this weird little jog here in the middle, and then goes down, hits a bottom point, and then shoots back up. So lots of weird things happen in the middle there, but the end behavior is as the x value moves further to the left, this goes down. As the x value moves further to the right, this goes up. I rescaled this so that it's a little bit easier to see. I used the x-axis going from like negative 11 to 11 and the y-axis going by jumps of like hundreds here. So if we rescale it, then you can see easily that we go up to that point, we go back down, we have a weird jog here. We go down to this point, and then we go back up. Again, end behavior is that as you move towards the right, you're going to positive infinity. As you move towards the left, you go out to negative infinity, but some weird things happen in the middle. So the end behavior is determined by the leading term, and then weird things can happen in the middle. So we saw that the end behavior of any polynomial function is determined by this leading term, the term of highest degree. And that tells you the end behavior of polynomial function. There's a lot of other features of these polynomial functions that we'll look at as we get into other sections. But this concludes what we're going to look at during this video on polynomial functions. We'll examine other features of polynomial functions in other videos.